Hi students, today we can solve one problem relating to the topic cache mapping. The question is, a byte addressable computer has a small data cache capable of holding 8 32-bit words. Each cache block consists of one 32-bit word. When a given program is executed, the processor reads data from the following sequence of hexadecimal addresses. And the given address sequence is like 200, 204, 208, 20C, 2F4, 2F0 and like this. The addresses are given in hexadecimal form. This pattern is repeated 4 times. For the execution of the program, this particular memory access repeated 4 times in the same sequence. Show the contents of the cache at the end of each pass through this loop if a direct mapped cache is used, and compute the hit rate for this example. Assume that the cache is initially empty. Okay, so for solving this, we need to understand some basic points like a byte addressable memory means each of the bytes of the memory is assigned with an address. Each of the byte of the given memory is assigned with an address. That is why a memory is called byte addressable memory. Next, here the addresses are given in hexadecimal form. So, we can convert this hexadecimal address into its binary equivalent form like this. For this particular address, its binary representation is this. Total how many bits required here for representing this particular byte address? 4 plus 4 plus 4, 12 bits. Okay, that means the physical address representation required total 12 bits of representation. So the question is, we need to perform the direct cache mapping here for the given address sequence. Okay, so given some more information like cache capable of holding 8 32-bit words. How many words? The capacity of the cache memory is here 8. 8 words it can hold. And the size of the word is 32 bits. 32-bit word means one word contains how many bytes? 4 bytes. So, such 8 words. Each word consists of 32-bit words or either 4 bytes. Such 8 words are present in our given small cache memory. And each cache block, the cache block can also be called as cache line. Each cache block or the cache line consists of one 32-bit word. Means in the cache memory, each cache line can hold one 32-bit word. So how many total cache lines present in the cache memory, in the given cache memory? Each cache line can hold one 32-bit word. How many such words are present in the given cache memory? Total 8 such words are present. So, how many cache lines are present? Total words in the cache memory divided by the cache line size. One cache line can hold one word. And total 8 words are available. So, 8 divided by 1, total 8 cache lines are present in our given cache memory. Like this. Total 8 cache lines. We can represent each of these lines like L0, L1 up to L7. Right. And the second point, each cache line can hold one word. One word here it is 32 bits in length. 32 bits means 4 different bytes are present in each of the words. The 4 bytes can be represented or addressed like 00011011. Okay, so we need to follow which mapping technique here? We need to follow first the direct mapping, and this is the given sequence. We need to access bytes with these given hexadecimal addresses, and we need to repeat 4 times. Okay, so for the direct mapping, the physical address can be considered as different blocks. What are they? The block offset part, line number part, and the tag field. So, in the given examples, in this given hexadecimal addresses, how many total bits are present? Total 12 bits are present. Means for representing each of these addresses, we need a minimum of 12 bits. Right. So, we need to identify among the 12 bits how many bits are needed for representing this block offset part. Okay. So, here in each of the cache line, we can hold a 32-bit single word. 32-bit single word means how many different bytes for different bytes. For addressing each of these bytes, how many bits are required? Addressing for different bytes means we need 4 different addresses. For generating 4 unique addresses, how many different bits are needed? 2 minimum bits are required for addressing 4 different bytes, and the addresses are like 00011011. So the block offset part contains how many bits? 2 bits. And for the line number, how many lines are present? 8 different lines are present. For addressing each of these 8 lines uniquely, how many minimum bits required here? 2 raised to 3 is 8. So 3 bits are required for this line number field. And 12 minus 3 minus 2 is 7. So 7 bits form the tag field. The remaining 7 bits form the tag field. So now we can consider or identify the block offset, line number, and tag field value of each of these hexadecimal address values like this. Okay, for 200, the block offset value is the 200. We can represent in binary. How? 2 can be represented in 4 bits, 0010. This 0 can be represented 0000. Thus 0000. So from these least 2 bits form block offset part. The next least after this block offset part, the next 3 bit from the LSB form the line number. Remaining 7 bit form the tag field value. Similarly, we can identify the block offset, line number, and tag field values of these address values also like these listed here. Okay, so based on this data, now we can identify number of hits and miss for the first pass now. Okay, so for the first pass, here the first address information or the first byte that we want, the processor want to access first is 200. Okay, so go here. Which line we need to, or in which cache line we need to store the byte addressed with value, address value 200, line number 0. So the word, 32-bit word that contains the byte with address 200, we need to transfer to line number 0 of the cache. At 00th byte position, we should have this byte 200 because the block offset value here it is 00. That means the 0th byte of that particular 32-bit word must be this particular byte having the address 200. Okay, so we can transfer a particular 32-bit word that holding the particular byte with address 200 into line number 0. Okay, so this is a case of cache miss. So next, 204, which is not present here. So for 204, we need to transfer that particular word would contain the byte with address 204 into which cache line? 001. That means line number 1. Okay, so we can transfer, and the byte with address 204 must be present in which byte position? 0th byte position. Okay, next 208. For 208, we need to transfer the word contain that particular byte with address 208 into line number 2. 010 is binary equivalent of decimal 2. Okay, so transfer that particular word into line number 2. Next, as address is 20C. 20C, we need to transfer into line number 3. Okay, and line number 3 with that particular byte with the address 20C must be present here in which byte position? The 0th byte position. Okay, next, this particular address 2F4, for this one we need to transfer that word contain this particular byte into which line? Line 101. 101 means line 5. Okay, next 2F0. 2F0 we need to transfer into line number 4. Next, so up to these all the cases are cache miss. With these 200 up to this 2F0 is not present here actually in the cache. So all these are the case of cache miss. Okay, the next accessing memory address is 200. But now the situation is different. The address is directly available in the cache memory. Right? So this is a case of cache hit. We don't want to transfer again from the main memory to the cache line because this particular byte with address 200 is directly available in our cache memory at which line? Line number 0. Okay, so next is 204, which is also directly available here in this cache. So this is a case of cache hit again. Next is 218, which is not directly available here now. So we need to transfer from our main memory to cache memory first. Okay, so for this 218, in which line we need to transfer into this particular line 110. 110 means line number 6. And this 218, the byte with address 218 must be present in block 0. Okay, because the block offset value is 00 here. Next is 21C. 21C we need to transfer into line number 7. Okay, next is 24C. This 24C we want to transfer into which line? Line number 3. But the line number 3 is already filled. Here we have no room for placing this particular byte with address 240. So in that case, what we want to do? We want to replace the current content of this line with the new content. So remove this particular memory word that which is present in line number 3 first. Then make a room here for holding the word that contains the address 24C. Now we can transfer. Okay, so this is again a case of cache miss. Next is 2F4. 2F4 is directly present here at line number 5. So this is a case of cache hit. So at the end of first pass, what is the status? How many hit and how many miss? Total 3 hit and 9 misses. So at the end of first pass, this is the case. 3 hit and 9 misses. Okay, so based on the current status, now we need to repeat it again. That means we need to start the second pass now using the same sequence of address information which is given in the question. Okay, so first here it is 200, so which is directly present here, so this is a cache hit. Again 204 present directly in the cache, so again a cache hit. 208 present here, again cache hit. Next is 20C. Is this 20C is available here? No. So this is the case of cache miss. Okay, so where we want to place this particular word contain this byte address 20C, look at here, we need to make a room at line number 3 here. So remove this particular memory word currently present in line number 3 first. Remove from this cache line and move to the main memory back. Then make a room here now and place the word that holding this particular byte address and place here in line number 3 now. Okay, so this is the case of cache miss. Next is 12-4 which is present, again a cache hit. 12-0 again a cache hit. 200 again a cache hit. 204 again a cache hit. 218 again cache hit. 21C again cache hit. 24C, as this 24C is present here? No, 24C is not present here. And where we want to make room for placing this 24C because the cache is fully filled now. So we need to make some room here for holding a word that contains the byte address 24C. Where we want to make space for holding this. So for identifying the line number, look at here. At line number 3, we want to make room. So whatever word present at line number 3 now, we need to remove from this position and place back into the main memory. Okay, now room is available here. And place the word that contains the byte address 24C into line number 3. Right? Next, so this is the case of actually a miss, cache miss. Next is 2F4 which is available here. Okay, so how many cache hit? Total 10 hit and 2 misses. Okay, so the same pattern that we have seen in pass 1 is repeated in pass 2 and pass 3. The same pattern repeated again in pass 2 and pass 3. Because we are asked to repeat 4 times the execution of this particular memory access. The sequence of memory access we are asked to repeat 4 times. Whatever values or whatever hit and misses present in pass 1 which is repeated again in pass 2 and pass 3. Okay, so we can conclude that in pass 2, how many hits are possible? 10 hit and 2 misses. Again in pass 3, 10 hit and 2 misses. So after completing the 4 execution, pass 0, pass 1, pass 2 and pass 3, this is the total hits and total misses. Right. So now we can calculate the hit ratio. The formula for finding the hit ratio is total hit divided by hit plus miss, total hit plus total miss into 100. The hit percentage. Okay, so total hit is 3 plus 10 plus 10 plus 10, that is 33 into 100 divided by 33 plus 9 plus 2 plus 2 plus 2, that is 33 plus 9 plus 2 plus 2 plus 2 is 48. So total hit ratio, hit percentage is 68.75. So this is the hit percentage in case of direct mapping, direct cache mapping. So we are also asked to repeat 4 times the same sequence of memory access, but here we are asked to follow which cache mapping method? 4-way set associative cache mapping. 4-way set associative means what? 4 words per set. Total 8 words or 8 cache lines are available here. So 4-way set associative means 4 cache lines per set. So total how many sets are possible here? Only 2 sets. Total 8, 4 sets, 4 lines per set. In set 0, 4 lines. Line 0 to line 3. In set 1, line 4 to line 7. We need to repeat the sequence 4 times and follow 4-way set associative cache mapping. Okay, so for this, we need to identify the block offset part, set number part and tag field. Total physical address contains 12 bits. And in each line or cache block or in cache line, how many bytes are present? 4 different bytes. For addressing each of these 4 bytes present in a cache line, how many minimum bits required? 2 bits. And how many sets are possible here? Only 2. For addressing these 2 sets uniquely, how many bits are required? Only 1 bit. This is represented using bit 0 and this is represented using 1. So total 2 raised to 0. 1 bit is required here. Okay. And sorry, 2 raised, not 2 raised to 0, 2 raised to 1. 2 raised to 1 means 2 different values possible like 0 and 1. Here 2 raised to 2, that is 4 different values are possible. And that 4 different values are used for addressing each of these bytes of our cache line. And remaining 12 minus 2 minus 1, that is remaining 9 bits act as the tag field value. The tag field values are used for identifying whether a particular requesting memory is present in the cache or not. Okay, now here we can identify for this address information 200, the least 2 bits from the block offset, next single bit from the set number and remaining 9 bits from the tag field. And similarly, we can identify this different field values for the given address sequences like this. Okay, so here this 200, we need to place it into which set? Set 0. And for the word that contains the byte address 204, we need to place it into set number 1. 208 into set number 0, 20C into set number 1 and so on. Okay, so we can start the memory access. Start with the sequence 200. Okay, 200, we need to move into which set? Set number 0. And in case of set associative, we can place anywhere in this set. Okay, if there any particular line is free here in this set 0, we can place a word into that free location. So here all the lines are free in set 0. So we can place this particular memory word that hold the byte address 200 into line number 0, the first free line of set 0. Next is 204. 204, we need to place it into set number 1. Anywhere in the set number 1. Here all the lines of set number 1 is free now. So we can place the first free line. So 204 into line number 4. Next is 208, where we can place this particular word contains the byte address 208 into set 0. Here The first line is already filled. So we can place anywhere here. The first line which is free now is line number 1. So place here. Next is this do not see, which is placed here. All these are the case of cache miss, right? Next is 2F4. We need to place it into set number 1. Next is 2F0. Place into set number 0. Again, it repeating 200. So this is the case of cache hit. Why? Because this particular memory word contains the byte address 200 is already available in set 0 at line number 0. So this is the case of cache hit. 204 already present here, again a cache hit. Next is 218. 218 we need to place it into line set 0 into a free line. So here we have the free location, so place here. Next is 21C, where we want to place into set number 1 and a free location in set number 1. Here we have one free location, so place here. Next is 24C. 24C, here we have no vacant space. 24C, we need a vacant space in which set? Set number 1. Okay, here now we have no vacant space. So in that case, what we want to do? We need to follow the least recently used algorithm for replacing a particular memory word from the cache memory. Which one is the least recently used line here or memory word here? For that, from this position, consider each address in backward direction and identify which address is least recently used. We need to make a room in set 1 for this particular address information. Okay. So in set number 1, 21C is used here. Next, 240 is used. Next, used set 1 address is 2F4 and 20C. So among these address information, this 20C is the least recently used address information of set 1. So we can move this particular word from line 5 back into memory and make a room here and place this newly requesting word into this particular line L5, right, based on LRU replacement algorithm. So this is again a cache miss. Next is 2F4. 2F4 is already available here, so this is cache hit, right? So at the end of first pass, this is the end of first pass. How many cache miss and how many cache hit? 3 hit and 9 misses. 3 hit and 9 misses. Okay, so this is the current status at the end of first pass. Now, based on this, we can start the second pass. Okay, so for this is a hit. This is again a hit available here in cache. This is again a hit. This is again, is this a hit? No, this is a miss. Okay, so where we place this do not see, we need to make a free room here in which set? Set 0 or set 1? For do not see, we need to make a free room here in set 1. So which particular line we can make free now? Here we need to follow the least recently used algorithm. So from this position, move backward and understand or identify the least recently used address information. So among this 204, 24C, 24C, 2F4 and 21C, which one is the least recently used address? From this position, 204 is used in a recent time. The next recently used is 24 and the next recently used is 24C. So the least recently used is 21C. So we can remove 21C from the cache at line number 7 now and make space for the word contains the byte address 20C. Right? So make room here and place the word that contains 203 into set number 1 at line number 7. This is the case of cache miss. Next is after 20C, next in the sequence is 12 which is present again cache hit. 12 cache hit, 200 cache hit, 204 cache hit, 218 again a hit. Next is 21C. Is this a cache hit? No. 21C is already replaced. So this is again a miss. Right? So what we want to do? From this position, consider each of these address in backward direction and identify the least recently used address. In which set? Set number 1. Because for 21C, we need a particular line in which set? Set number 1. So we need to make a room here. Okay, where we want to make the room, we want to free particular line which is holding a word that is least recently used. For getting that least recently used address, what we want to do, we need to consider each and every address in backward from this particular position. So in set number 1, now the address available are 204, 24C, 2F4, 20C. Among these, which one is the least recently used? 240 is recently used. Next, recently used from set 1 is 2F4. Next is 20C. So again, here it is 204, 2F4. So the least recently used is 24C. So from line number 5, we can remove this particular word holding the byte 24C and move it back into memory and make here a room for passing the word that contains the byte address 21C. Okay. So this is a case again, a cache miss. So after 21C, next is 24C. As this 24C is available, again 24C, we need a space here in set number 1. 24C is not present, so again a cache miss. Right? So again follow the least recently used replacement algorithm for making a room for this 24C. So from this position, consider each and every address in backward direction and identify the least recently used one. 21C is used recently. 204 is used recently. Next is 2F4 is used recently. So it is clear that 20C is the least recently used address in set 1 now. So we can replace this particular word contained 20C and move back into memory and make a room here for holding the word that contains the byte address 24C. This is again a case of cache miss. So after that 12F4. 12F4 is available. So this is a cache hit. So at the end of second pass, how many hit and how many miss in second pass? 3 misses and 9 hit. 3 misses, 12 minus 3, 9 hits. Right? So the same pattern repeat in pass 2 and pass 3 also. So total miss and hit. In pass 0, 9 miss and 3 hit. Pass 1, 3 miss, 9 hit. Pass 2, 3 miss, 9 hit. Pass 3 again, 3 miss, 9 hit. So we can calculate the hit ratio or hit percentage like hit into sorry, total number of hit divided by total number of hit plus total number of miss into 100. This into 100 is for getting the percentage of hit. Okay, so total number of hit, here it is 9 plus 9 plus 9 plus 3 is 30. 30 divided by 30 plus this much 80 into 100. So this is 62.5 percentage. Okay, so this is the solution for the given sequence of memory access. That particular memory access is repeated 4 times. The first case is based on direct cache mapping and the second one is based on four-way set associative cache mapping. Okay, thank you.